Let's be honest, the real world isn't neat and tidy. It's messy, it's unpredictable, and it almost never gives us all the information we need. So when we try to build smart systems, we're constantly fighting against this wave of uncertainty. But what if, instead of fighting it, we could actually learn to work with it?
That's the huge question we're tackling today. How do we build systems that don't just shut down the second they run into the ambiguity of real life? You see, classical models, they demand perfection. But the world, well, it rarely cooperates.
So our traditional ways of modeling things are incredibly powerful, don't get me wrong, but they have one big weakness. They're built on the assumption that our data is perfect, complete, and super precise. And as anyone who works with complex systems knows, that's just almost never true.
For starters, real-world systems are just swimming in uncertainty. Think about trying to predict the stock market or even just controlling a robot arm in a room where things are moving around. There are always these variables we can't perfectly measure, and that's a huge problem for rigid, old-school models.
And on top of that, there's the problem of incomplete or sparse information. Maybe we only have a handful of data points to go on, or maybe some of our sensor readings are missing. Trying to build a precise model from a spotty data set, it's like trying to solve a jigsaw puzzle when you know for a fact you're missing half the pieces.
And then there's the really tricky part, unmodeled dynamics. You see, some behaviors are just too complex to fit into a nice, clean mathematical equation. These are kind of the hidden forces, the subtle interactions that can make a system do something completely unexpected.
Okay, so faced with all this messiness, this uncertainty and incompleteness, how do we possibly move forward? Well, the answer isn't to just wish for better data. The answer is to build smarter tools. Today, we're going to dive into two really powerful frameworks designed for exactly this challenge: fuzzy systems and gray systems.
So our first approach kicks off with a really interesting idea. What if we stop trying to force the world into a black and white yes or no box? What if we just embrace the fact that most things in life actually exist in, well, shades of gray?
And that brings us to the world of fuzzy systems. Instead of that strict binary logic where something has to be 100% true or 100% false, fuzzy logic allows for degrees of truth. It's built from the ground up to understand and process imprecise, human-like concepts, the kind of language we use every single day, like saying it's kind of warm or you're driving pretty fast.
Here is the absolute best way to think about it. A classical system is like a standard light switch. It's either completely on or it's completely off. There is zero in between. A fuzzy system, on the other hand, is like a dimmer switch. It can be 10% on, 45% on, 80% on. It handles that entire spectrum, which, let's be real, is much closer to how the world actually works.
So how does it actually pull this off?
Well, it's basically a three-step process. First, in fuzzification, you take a precise input, let's say a temperature of exactly 23 degrees, and you convert it into fuzzy ideas like cool and warm. Next, an inference engine uses a set of simple if-then rules, kind of like if the room is warm, then turn the fan to medium. And finally, in defuzzification, that fuzzy decision gets translated back into a crisp, precise command, like setting the fan speed to exactly 1500 RPM.
Okay, so that's how we can handle vagueness. Pretty cool, right? But what about a totally different kind of problem? What do you do when your information isn't vague, you just don't have enough of it to begin with?
And this is exactly where gray system theory comes into play. It's a framework specifically designed for those situations where you have incomplete info or maybe just a few data samples. The whole goal is to squeeze as much insight as possible out of very little data so you can still make reliable predictions.
Think of how much we know about a system as a spectrum. On one end, you've got a white box, where you know absolutely everything about how it works, every equation, every little detail. On the total opposite end is a black box, where you know nothing about what's going on inside. Gray system theory lives in that huge, practical middle ground of the gray box, where we have some information, but definitely not the whole picture. And honestly, that's where most real-world problems are.
So we have two really powerful tools for dealing with uncertainty, but, and this is super important, they're not interchangeable. They're designed for very different kinds of problems. And figuring out that difference is the key to knowing which one to use.
The distinction is simple, but it's absolutely critical. Fuzzy systems are your go-to for vagueness, for translating those human-like rules into logic. Think of a smart thermostat that adjusts because the room feels a bit chilly. Gray systems, on the other hand, are built to tackle incompleteness. They're perfect for making predictions when you have very little history to go on, like forecasting sales for a brand new product launch. So why does all this matter? What's the big deal? Well, by giving us a way to actually model this imperfect world we live in, these tools unlock a huge range of powerful, real-world applications.
And we're not just talking about abstract theories here. This stuff is being used right now for smarter decision-making in business, for more accurate financial predictions, and for advanced diagnostics to figure out when complex machines are about to break. It's essential for building robust control systems, and it's even helping us get a handle on modeling complex social systems.
You know, this quote from Richard Hamming really just gets to the heart of it all. Fuzzy and gray systems remind us that the end goal isn't just to crunch perfect numbers. The real goal is to gain insight into how the world actually works, even, and maybe especially, when the numbers we have are far from perfect. They are tools for understanding, not just for calculating.
So as these tools get even better and more sophisticated, it leaves us with this really fascinating question. Now that we have the ability to model systems that are vague, uncertain, and incomplete, what previously unsolvable problems are suddenly within our reach? What new frontiers in science, in engineering, and in our society can we now finally begin to explore?